Hi class, welcome back. Today we'll be doing chapter 13, WAN connectivity. This is a little bit of a recap, but the book talked about it this week, so I'm going to go ahead and cover it again really quick. LAN, local area network, consists of a series of computers that are linked together, usually in a close geographical area. You can use TCP, IP, Ethernet, you can use Wi-Fi, either way, totally fine for a LAN connection. A WAN is a wide area network, so it's a series of LANs linked together, or at least this is how CompTIA defines it. Let's talk a little bit about WAN technologies. Interconnection before SONET was outlandishly expensive, and the internet, at least as we know it today, probably would not exist without this technology coming around. Again, it came out a fairly long time ago, so the first implementations of SONET were in about 1987. Primarily fiber optic carriers moved to a new international standard. In the United States, we call this synchronized optical network, SONET. Synchronized optical network, SONET. However, Europe and most of the rest of the world use something called SDH, synchronous digital hierarchy. Synchronous digital hierarchy, SDH. So most of the rest of the world used this right here. The United States used SONET. Even though the two technologies were a little bit different, the two standards were a little bit different, the networking devices used at the time could easily exchange data between the two technologies. Let's talk about the importance of SONET. It's a standard for long-distance, high-speed fiber optic transmission. It defines the OSI interface standards for the physical and data link layers. Some of the physical aspects of SONET are partially covered by the optical carrier standards. It defines a ring-based topology for SONET adopters. Here's where things get a little bit tricky. SONET does not require a ring, but many telecommunication networks are SONET rings. This type of ring technology has fault tolerance in the case of a line loss. So in the early chapters, we talked about a kind of classic ring technology, and I warned you guys that if you get online, you're going to get some confusing things where different types of ring topologies have fault tolerance, and some don't, some do, some don't. This is one of the cases where a SONET type ring technology or topology will have fault tolerance built into the system in case of a line loss. There have been a number of improvements in fiber optic technologies over the years. One super important innovation has been dense wavelength division multiplexing, DWDM, dense wavelength division multiplexing. This enables an individual single mode fiber to carry multiple signals. So an individual single mode fiber can carry multiple signals. It gives each signal a different wavelength, uses different colors of laser lights, can support 150 signals, and it is very popular for long distances. I have an analogy for it. It's not the greatest analogy in the world, but I think it kind of helps me visualize what this is talking about. Imagine you hear a whole group of people singing all in harmony, all together. It's kind of hard to pick out any individual person's voice out of that whole group. However, if you had one person singing at a very low wavelength, a baritone kind of wavelength, and then another individual singing at a very high sort of soprano wavelength, it would be easy to pick up on those individual sounds coming from those people. That's kind of what's going on here, except for these computers are doing it with light. Another advantage of this is something called bidirectional wavelength division multiplexing, WDM or BWDM. And all this is that if we can send multiple signals by dividing the wavelength in one direction, we could probably use some of those to go the other way. We just talked about dense wavelength multiplexing. We're going to talk about coarse wavelength division multiplexing now, CWDM. Essentially a very similar concept. You rely on multiple wavelengths of light to carry fast signals over long distance. It is simpler than DWDM. It offers lower cost as a major benefit, and the practical distance limit of this is 60 kilometers. So again, one of the key differences though between dense wavelength division multiplexing and coarse wavelength division multiplexing is the number of signals that you can get on there. Dense, we're packing as many signals as we possibly can, and coarse, we have fewer kind of wider signals that we're using for that technology. So again, dense, more signals, more expensive. Okay, up next, we're going to talk about something called private WANs. This is a concept that is often referred to as a leased line. a leased line. They have a dedicated connection from the telecommunication company. So that is basically the main idea here. We have a dedicated connection of some kind from the telecommunication company. This is not your everyday average person that's going to get this. This is usually something for a bigger business or a bigger organization. They tend to be fairly expensive, but again, ideal for many bigger businesses. There's a few key technologies that we use to provide private WANs. One is MPLS. We're going to talk a bunch about this. We have SD-WAN. We're going to talk a little bit about that, and Metro Ethernet. One advantage of a private dedicated WAN is that they tend to be much more secure and offer more secure network communication with less fear of hackers accessing network resources. MPLS, multi-protocol label switching. Multi-protocol label switching. Essentially, this is a router feature that labels certain data to help improve the flow of traffic on your network. It provides a platform-agnostic labeling system that greatly improves IP network router-intensive performance. The idea here is that we add an MPLS label that sits between the layer 2 and layer 3 headers. We're going to look at that here in a second. MPLS header parts. So we mentioned before, we have our layer 2 header here and our layer 3 header here, and our MPLS header is just kind of sandwiched in between those. There are 4 parts to it that we're going to talk about: the label, the experimental bits, the stack, and the TTL. The label is a unique identifier that helps MPLS capable routers determine how to move the data. The experimental bits, this is relative value defining the importance of the labeled packet for prioritization. The stack, so sometimes there are multiple labels kind of sandwiched between the layer 2 and layer 3 header, and this will just let the devices that are handling it know which label in the stack that they're dealing with. It is set to 1 for the initial label. TTL, this is a term we've heard before, and in this case it means basically the same thing. It's just the maximum number of hops before the label is eliminated. It stands for time to live. And we're just going to kind of bullet point some of the main points to the MPLS process. Network traffic moves more quickly and efficiently when you're using MPLS routers. Provides network-wide quality of service. MPLS-capable routers avoid running IP packets through their full routing tables. Use header information to route packets quickly. Quality of service spans the entire group of routers. Use existing dynamic routing protocols. So it uses existing dynamic routing protocols. MPLS routers talk to each other about their overhead. So again, we have our little diagram here that kind of depicts that idea. So maybe traffic is consistently being routed through this specific device right here, and it can kind of comically communicate with the other routers on the network and say, hey, I'm being overburdened, try to choose another route if you can. And it will dynamically sort of on the fly manage that traffic more efficiently to improve the quality of service. Let's talk about a few MPLS terms. One would be forwarding equivalency class, FEC. It's a set of packets that can be sent to the same place. So again, you could maybe think of it, if you were given a bunch of mail to delivery, it might be efficient to kind of pile all the things that can be sent together to the same destination and send them all at the same time. It's kind of the idea, or at least sort of roughly the idea behind that. Label switching router, LSR. These are essentially just routers that look for and forward packets based on their MPLS label. Basically just routers that are capable of dealing with these MPLS things. We also have label edge router, LER, MPLS routers that can add MPLS labels to unlabeled packets. So again, the difference here is these are sort of the routers that sit at the edge of your network, and when they receive data that's going inside your network, they can add those labels to it, and then when they're receiving packets that are going out of your network, they can strip those labels off and send it out to the regular internet. The last term we're going to talk about is LDP, Label Distribution Protocol. LSRs and LERs use LDP to communicate dynamic information about their state. So again, this is basically just the protocol that these routers use to communicate and update each other about what their current status is. This is an image that might kind of help you picture what's going on. We have a little network here, and as we can see, there's multiple paths. We have our LERs. These, again, are the routers that are capable of dealing with these labels that are on the edge of your network. And then we have these LSRs in the middle. These are, again, just routers that are designed to help kind of pass those labeled or MPLS labels along throughout your network. Okay, let's do a quick rundown of the sort of textbook process that's going on here. When an MPLS network comes online, the administrator will do some sort of initial configuration and initial setup. They may put in some kind of metrics or data that helps the routers manage traffic fairly efficiently. The LERs have most of the power in determining the route, or a lot of power in determining the route. And that's the outside ones, because they're receiving the packets initially that are coming in and out of the network. They're adding these initial labels to them and removing the labels when they go out. There's some disadvantages of MPLS. One disadvantage is the backhaul connections will be slow, expensive to acquire, and install dedicated connections between central offices and the various back offices or satellite locations. So again, if you have a main center where your business is running, or the company or organization is running, and then a lot of satellite or remote locations, it is very hard to do this kind of system. Very expensive and very difficult to set up. This enables traffic over the internet to incorporate a lot of the features of MPLS. It has efficient addressing and routing, maintains high security, and it relies on virtualization technology. So that is SD-WANs in short. We're going to talk more about these later on in the textbook, so we're not going to do a ton of depth on that right now. Metro Ethernet creates a secure private network within a city. This uses fiber optic or Ethernet technology. CompTIA will refer to this technology as Metro Optical. This will create when we use this technology, we create a metropolitan area network, MAN. So the same way we have LAN, WAN, we have MAN. Does not use an internet connection and does not require security, allegedly. The cost of implementing this using Ethernet is generally cheaper compared to the MPLS technology or the SD-WAN technology. Up next, we have last mile technologies. These are connection options from the teleco central office to a premises. I think the way your textbook likes to describe this as on-ramp technology. If we were picturing a freeway as this sort of very fast, optimized way that we're moving cars or traffic along, at least in a perfect world, ideally, then this would be the kind of on-ramp or from the freeway to your house type technology. There's a few that we're going to cover in a lot of detail here: DSL, cable, fiber, satellite, and cellular. First up on the list, DSL. This stands for Digital Subscriber Line. It is fully digital, has a dedicated connection. It's a great advance from the older ISDN technology. It uses a PSTN connection, public switched telephone network. So we're using the same telephone lines and RJ11 jacks that we would for a standard phone line. There's two versions of DSL that we're going to talk about: asymmetric DSL and symmetric DSL. So asymmetric DSL and symmetric DSL. Symmetric DSL provides the same upload speeds and download speeds. So that is the key idea there. That's what makes it symmetric. The upload speeds and download speeds are the same. You can have theoretical speeds of up to 15 megabytes per second. Realistically, most ISPs will offer something closer to this range right here. Asymmetric DSL, on the other hand, is a lot more practical for most end users. Your download speeds are going to be much faster than your upload speeds. It is generally much less expensive than symmetric DSL. Okay, here's some key DSL features in kind of a bullet point format. The same phone lines carry the data and voice. So it's the same phone lines for data and voice. The distance restriction is 18,000 feet from the central office if you're not using any repeaters. So again, you can overcome that with some technology out there like repeaters, but the natural maximum distance is 1,800 feet or 18,000 feet from the central office. DSL access multiplexer, the DSL AM, DLS access multiplexer, DSL AM, located at the central office, connects multiple customers to the internet. There's 3 channels for the DSL line: a high-speed downstream line, a medium-speed duplex line, and a plain old telephone service, POTS, plain old telephone service. This is what this would kind of look like. Again, you need a POTS filter between your phone and the main line. So again, you'll have one line that comes into the wall jack, one will split off into a DSL modem that will go to your end device. The other end of the line will go to a POTS filter that will again filter out some of the DSL signals and give you something for your plain old telephone to use. DSL installation, a little bit more on this. The first generations used what's called a bridged connection. No authentication was required. You just kind of simply connect to the internet through your modem. Later on, they came up with a point-to-point over Ethernet, PPPoE. This is preferred by the ISP because it gives them a little more control and a little more ability to see what's going on. It requires a username and a password. Most SOHO routers have PPoE support. Okay, up next we have Broadband Cable. This is added service from the cable TV providers. Cable TV industry modified their infrastructure. Cable modems are now very, very common. Theoretical speeds are anywhere from 5 megabytes per second up to 1.2 gigabytes per second. So again, much, much faster than what we had going on with DSL. The service quality varies by provider and region. So again, realistically, you could get a whole range of different speeds. These are fairly common or a fairly reasonable expectation of what you might get. Cable modem installation. So this is what that network might that network setup might look like. Something like this. A cable modem connects to an outlet via a coaxial cable. The line is just split from the main line as if adding a second cable outlet that is separate from the TV line. The cable modem then connects to a router, in turn connects to a PC using standard NIC and UTP cabling. DOCSIS. This is Data Over Cable Service Interface Specification, DOCSIS. This is a cable network protocol. The current version is DOCSIS 4.0. Some of the differences between a cable modem and a DSL modem would be the connectors. So a cable modem has a coax F type connector. We talked about that in previous chapters, and an RJ45 connector. A DSL modem will have the old phone cable style connector, an RJ11 connector, and a RJ45 connector. All right, let's talk about satellite. It's the only option for some remote locations. There's a couple types. There's one-way, download from the satellite and upload using the PSTN dial-up connection. And then there's two-way, download and upload via satellite. Requires satellite antenna, connects to satellite modem. The modem connects to the PC NIC or network. And this is what that setup might look like, something like that, or at least at a very simple level. Let's talk about fiber optic as a kind of fiber to home or fiber to the premise last mile option. So DSL, again, it's not completely phased out. It's more popular and used more often than you might expect in a lot of regions in the United States and throughout the world in general. However, cable modems, again, are kind of taking over most of the market, or at least were for a long time. And so telephone providers wanted to start rolling out fiber as a way to kind of compete with the people who are interested in the higher speed, faster connections. So we have fiber to the home or fiber to the premise as an alternative to cable internet. US providers are AT&T and Verizon Fios, for some of the bigger providers anyway. It offers bidirectional 1 gigabit throughput. There are some people who offer, again, not telephone providers, but just internet-only fiber offerings. One of the big ones is Google Fiber. Again, it connects at 1 gigabyte per second. So one of the ways they're kind of keeping costs down is that using this passive optical network or PON architecture. We use a single fiber to the neighborhood switch, and an individual fiber runs to each destination. They use WDM, which is wavelength division multiplexing. We were talking about that before, and this enables multiple signals to travel over the same fiber. Cellular WAN, voice and data used on smartphones. We're moving voice and data information through a cellular wireless network with towers that cover the world. Again, an exception for when we're using Wi-Fi or our devices on Wi-Fi networks. There's 6 common terms that we're going to focus on: GSM and EDGE, CDMA, HSPA+, LTE, and 5G. GSM and EDGE, Global System for Mobile Communications, GSM. Global System for Communications. First networking technology widely applied to mobile devices. Relies on time division access. Multiple users share the same channel at the same time. Time division multiple access. TDMA. Introduce subscriber identity module, SIM card, SIM, SIM cards, subscriber identity module. Now ubiquitous with smartphones, identifies the phone, enabling access to the network. We have a little image here of the older style SIM cards and a quarter to kind of give you a size comparison of what that would look like. GSM and EDGE. GSM was considered a 2G technology. As it continued to improve over the years, they would often give it newer names. So enhanced data rate for GSM evolved into EDGE. So that was the kind of newer version of the GSM technology. One of the last GSM standards offered data speeds of up to 384 kilobytes per second. CDMA, Core Division Multiple Access, came out not long after GSM, used a separate spectrum form of transmission, totally incompatible with the GSM TDMA technology. Transmission changed frequencies used by each user. So you would change the frequency used by each user. It was considered by many to be superior to GSM. Most US carriers adopted the CDMA technology. However, almost everybody else in the world continued to use GSM, created a lot of compatibility issues and a lot of problems. One other note is CDMA lacked the SIM cards. So there were no SIM cards on the CDMA technology. IMT 2000, International Mobile Telecommunication 2000 Standard, or just IMT 2000 Standard. This was designed to address the shortcomings in mobile technology that were kind of widespread at that point in time. So we got higher speeds, full-time internet, multimedia messaging, and a lot of other critical functions. 3G was originally meant to mean that was compliant with the IMT 2000 standards, but it was kind of a mess at that time and not always the case. It was largely incongruent and inconsistent. The last of the 3G standards was Evolved High-Speed Packet Access, HSPA. HSPA, High-Speed Packet Access, is the, again, final 3G data standard. LTE, Long-Term Evolution Technology, LTE, introduced in early 2010s. Dominates wireless services, marketed as true 4G technology, download speeds of up to 300 megabits per second, upload speeds of up to 75 megabits per second. These LTE services use SIM cards. They're different than the other ones that we've talked about. So here we can see the nano SIM card compared to a quarter to kind of get a size aspect of that. It's also easy to add LTE service to different devices. They sell these little USB drives that you can stick into a laptop or different devices to make them connect to an LTE network. 5G started rolling out in 2019, has 3 bands, a low band that runs at 600 to 800 megahertz, similar to 4G, medium band that runs at 2.5 to 3.7 gigahertz, and then a high band that runs at 25 to 39 gigahertz. The higher the frequency, the faster the possible throughput speeds, the shorter the range. So again, the higher the frequency, the faster the throughput speeds, the shorter the range. 5G expected speeds, somewhere in the range of 30 megabytes per second up to 1 gig up. High band 5G implementation needs dense saturation of transmitters, receivers, and antennas. Works best in dense settings. It's a viable replacement to many other networking technologies. The final section this chapter in the book covers is remote access. So it'll talk about things like VPNs, RDP, all that kind of stuff. And I definitely think it's worth taking the time to read. But that is all I have for this week. I hope you enjoyed this video and I hope you have a wonderful day. Bye.